So I've been talking for like more than 5 minutes, and now I have to start talking again because I realized you can't hear me. Great, that's called paying attention to things and being super careful. I'm really sorry. I'll start again. I'll start over. I'll talk again. All the other words I said. The first word was hello world. I've been literally talking for 5 minutes. Okay. And I said really cool things. Now I don't know how to repeat them. I've been talking, I said hello world, and I said good morning, good evening, good whatever time of your day is. And I said, no worries, welcome. I said that it's been 2 weeks, yesterday, if we count it, and it feels like I've been doing this more than 2 weeks. I thought it was 3, but it's only been 2 weeks. I guess it becomes sort of a habit. So the recap is, we are doing Introduction to Machine Learning for Coders, taught by Jeremy Howard on fast.ai, and it says that it's a 12-week course. Because we've been studying it on daily for the past 2 weeks, we're in lesson 5. We've finished lessons 1 to 4, and I was saying how the cool thing is in lesson 5, today we're going to start with the random forest from scratch. I think that will be really interesting, and it is 12 lessons, and I really hope that we can finish in if not 8, but 10 weeks. I think that would be really cool, because there are other courses that maybe I want to take. I'm not sure. So that would be pretty cool. And then the other thing is, let's start, I suppose.
And we're going to come back and build our own random forest. I just wanted to clarify something quickly. Very good point during the break was going back to the change in R squared between here and here. It's not just due to the fact that we removed these 3 predictors.
Mm-hmm.
We also went reset RF samples.
Oh.
Right? So to actually see the impact of just removing, we need to compare it to the final step earlier. So it's actually compared to 907. So removing those 3 things took us from 907 to
9-1?
915. Okay, so I mean, and in the end.
So instead of having the 50k samples, we're looking at the whole database. That's why the difference seems so big.
Of course, what matters is our final model. But just to clarify. Okay. So some of you have asked me about writing your own random forests from scratch. I don't know if any of you have given it a try yet. My original plan here was to do it in real time, and then as I started to do it, I realized that would have kind of been boring for you because I screw things up all the time. So instead, we might do more of a walk through the code together. Just as an aside, this reminds me, talking about the exam, actually somebody asked on the forum about what can you expect on the exam. The basic plan is to make it the exam be very similar to these notebooks. So it'll probably be a notebook that you have to, get a data set, create a model, train it, feature importance, whatever, right? And the plan is that it'll be open book, open internet. You can use whatever resources you like. So basically, if you're
That's cool. I love open book exams, especially open internet exams.
entering competitions, the exam should be very straightforward. I also expect that there will be some pieces about like, here's a partially completed random forest or something, finish writing this step here, or here's a random forest, implement feature importance, or implement one of the things we've talked about. So it'll be, the exam will be much like what we do in class and what you're expected to be doing during the week. There won't be any define this or tell me the difference between this word and that word or whatever. There's not going to be any rote learning. It'll be entirely like, are you an effective machine learning practitioner? I.e., can you use the algorithms? Can you create an effective validation
Not an exam of can you memorize things well.
set, and can you create parts of the algorithm, implement them from scratch? So it'll be all about writing code, basically. So if you're not comfortable writing code to practice machine learning, then you should be practicing that all the time. If you are comfortable, you should be practicing that all the time also. Whatever you're doing, write code to implement to do machine learning. Okay. So I kind of have a particular way of writing code. And I'm not going to claim it's the only way of writing code, but it might be a little bit different to what you're used to, and hopefully you'll find it at least interesting. Implementing random forest algorithms is actually quite tricky, not because the code's tricky. Like, generally speaking, most random forest algorithms are pretty conceptually easy. Generally speaking, academic papers and books have a knack of making them look difficult, but they're not difficult conceptually. What's difficult is getting all the details right and knowing when you're right. And so,
Okay, I don't know what that means, but let's see.
in other words, we need a good way of doing testing. So if we're going to re-implement something that already exists, so like say we wanted to create a random forest in some different framework, different language, different operating system, I would always start with something that does exist, right? So in this case, we're just going to do it as a learning exercise, writing a random forest in Python. Mm-hmm. So for testing, I'm going to compare it to an existing random forest implementation. Okay, so that's like critical. Anytime you're doing anything involving like non-trivial amounts of code in machine learning, knowing whether you've got it right or wrong is kind of the hardest bit. I always assume that I've screwed everything up at every step. And
whoa, that's literally the mindset I have at life. I always think I'm doing it wrong and someone's going to figure it out with everything. Wow, I didn't realize we're so similar.
So I'm thinking like, okay, assuming that I screwed it up, how do I figure out that I screwed it up? Right? And then much to my surprise, from time to time, I actually get something right, and then I can move on. Okay, but most of the time I get it wrong. So unfortunately with machine learning, there's a lot of ways you can get things wrong that don't give you an error. They just make your result like slightly less good. And so that's what you want to pick up. So given that I want to kind of compare it to an existing implementation, I'm going to use our existing data set, our existing validation set, and then to simplify things, I'm just going to use 2 columns.
This is lesson 3. I'll have to find lesson 3. Anyway, let's just look for now.
To start with. So let's go ahead and start writing a random forest. So my way of writing nearly all code is top-down, just like my teaching. And so by top-down, I start by assuming that everything I want already exists, right? So in other words, the first thing I want to do, I'm going to call this a tree ensemble, right? So to create a random forest, the first question I have is...
A tree ensemble as in a list of trees, which means a forest. So we have XY, which is the list of columns, features, and then the target. How many trees do we want to make? I don't know what SZ stands for. S. There's the thing that I forgot that was there. Anyway. And then min leaf. create tree, decision tree. Oh, so we do have a thing called decision tree that we can return. It's not errors though, right?
What do I need to pass in, right? What do I need to initialize my random forest? So I'm going to need some independent variables, some dependent variable, pick how many trees I want. I'm going to use the sample size parameter from the start here. So how big do you want each sample to be? And then maybe some optional parameter of what's the smallest leaf size. Okay.
Okay.
For testing, it's nice to use a constant random seed, so we'll get the same result each time. So this
It says 42. I love the number 42. Because, Hitchhiker's Guide to the Galaxy.
is just how you set a random seed. Okay. Maybe it's worth mentioning this for those of you who aren't familiar with it. Random number generators on computers aren't random at all. They're actually called pseudo-random number generators. And what they do is, given some initial starting point, in this case 42, a pseudo-random number generator is a mathematical function that generates a deterministic, always the same, sequence of numbers, such that those numbers are designed to be as uncorrelated with the previous number as possible.
So...
and as unpredictable.
Okay, uncorrelated with the previous. Oh, that doesn't make it random, because random numbers can be, like when you flip, flip a coin, the possibility of it being duplicated is not low, so that doesn't make it random if it's always different.
As possible. And as uncorrelated as possible with something with a different random seed. So the second number in the sequence starting with 42 should be very different to the second number starting with 41. And generally they involve kind of like taking, using big prime numbers and taking mods and stuff like that. It's kind of an interesting area of math. If you want real random numbers, the only way to do that is that you can actually buy hardware called a hardware random number generator that will have inside them like a little bit of some radioactive substance and like something that detects.
Physical/chemical randomness. Does anyone know about the wall? There's a wall of lamps. I think it's in somewhere in Europe that has to do with security encryption and yeah, that's cool. There's a wall of lava lamps for encryption that there's a Tom Scott video about it. So if we say Tom Scott lava lamps, yeah, they keep the internet secure. Like if I just Google image it instead of, there's a camera on them, and because they're pretty random. Yeah, encryption lava lamps. Oh, it's in San Francisco. I thought it was in Europe. Anyway, so yeah, randomness. It's really hard to fake.
How many things it's spitting out, or there'll be some hardware thing.
Getting current system time, is it a valid random number generation process?
So that would be maybe for a random seed, right? So this thing of like, what do we start the function with? So one of the really interesting areas is like in your computer, if you don't set the random seed, what is it set to? And quite often people use the current time for security. Like obviously we use a lot of random number stuff for security stuff. Like if you're generating an SSH key, it needs to be random. It turns out people can figure out roughly when you created a key. Like they could look at IDRSA has a timestamp, and they could try all of the different nanoseconds starting points for a random number generator around that timestamp and figure out your key. So in practice, a lot of really random high randomness requiring applications actually have a step that say, please move your mouse and type random stuff at the keyboard for a while.
Wow.
And so it like gets you to be a source. It's called entropy, to be a source of entropy. Other approaches is they'll look at like, the hash of some of your log files, or stuff like that. It's a really, really fun area.
Mm-hmm.
So in our case, our purpose actually is to remove randomness. So we're saying, okay, generate a series of pseudo-random numbers starting with 42. So it always should be the same. So if you haven't done much stuff in Python OO, this is a basically standard idiom. At least, I mean, I write it this way. Most people don't. But if you pass in like 1, 2, 3, 4, 5 things that you're going to want to keep inside this object, then you basically have to say self.x equals x, self.y equals y, self.sample equals sample. Right, and so we can assign to a tuple from a tuple. So, again, this is like my way of coding. Most people think this is horrible, but I prefer to be able to see everything at once. And so I know in my code, anytime I see something that looks like this, it's always all of the stuff in the method being set. If I did it a different way, then half the code's now come off the bottom of the page and you can't see it. So
true. If you do one by one, it will look longer, but yeah, both is fine.
All right. So so that was the first thing I thought about, was like, okay, to create a random forest, what information do you need? Then I'm going to need to store that information inside my object. And so then I need to create some trees. Right? A random forest is something that something that has some trees. So I basically figured, okay, list comprehension to create a list of trees.
Mm-hmm.
How many trees do we have? Well, we've got n trees. That's what we asked for. So range n trees gives me the numbers from 0 up to n trees at -1. Okay. So if I create a list comprehension that loops through that range, calling create tree each time, I now have n trees.
Okay.
And now, so I to write that, I didn't have to think at all. Like, that's all like obvious. And so
yeah, but the tree hasn't been created yet. It's a function down here.
I've kind of delayed the thinking to the point where it's like, well, wait, we don't have something to create a tree. Okay, no worries. But let's pretend we did. If we did, we've now created a random forest. Okay.
I love creating functions without bodies and just say, let's pretend it works.
Still need to like do a few things on top of that. For example, once we have it, we would need a predict function. So, okay, well, let's write a predict function. How do you predict in a random forest?
Mm-hmm.
Can somebody tell me, either based on their own understanding or based on this line of code, what would be like your 1 or 2 sentence answer? How do you...
Mean. I see mean. So it's the mean of the, the tree that we saw last time. Mean of y. Is it, what, it says x? I mean, t predict, I don't know where t is coming from. So I'm guessing it's an already existing thing. Oh no, it's just the trees. Okay, then I guess the decision tree has predict. So we are meaning the y's. Yep.
How do you make a prediction?
TDD start with writing test first. What do you mean by TDD? Test driven something. I see what you mean. Yeah. I don't know if it's writing test first or it's just lazy coding. Test driven development. Got it. Yeah. Yeah. Thank you. I think on my part it's lazy coding. Yeah. But I guess test driven development is also a pretty cool thing.
A random forest. Possible, Spencer?
You would want to, over every tree for your, like the row that you're trying to predict on, average the values that each tree would produce for that.
Exactly,
that
good. And so, that's a summary of what this says, right? So for a particular row, right, or maybe this is a number of rows, go through each tree calculate its prediction. So here is a list comprehension that is calculating the prediction for every tree for x. I don't know if x is one row or multiple rows. It doesn't matter, right? As long as tree.predict works on it. And then once you've got a list of things, a cool trick to know is you can pass numpy.mean, a regular non-numpy list, okay? And it'll take the mean. You just need to tell it axis equals 0, means average it across the lists. Okay, so this is going to return the average of dot predict.
Axis equals 0 means it's a list. Anyway, okay.
For each tree. And so I find list comprehensions allow me to write the code in the way that my brain works. Like, you could take the words Spencer said and like translate them into this code, or you could take this code and translate them into words like the one Spencer said, right? And so when I write code, I want it to be as much like that as possible, right? I want it to be readable. And so hopefully you'll find, like when you look at the fast.ai code and you're trying to understand, well, how did Jeremy do X? I try to write things in a way that you can read it and like kind of turn it into English in your head.
That's cool.
So if I see correctly, that predict method is recursive? It's
No, it's calling tree.predict, and we haven't written a tree yet. So self.trees is going to contain a tree object. So this is tree ensemble.predict, and inside the trees is a tree, not a tree ensemble. So this is calling tree.predict, not tree ensemble.predict. Good question. Okay. So we've nearly finished writing our random forest, haven't we? All we need to do now is write create tree. Right? So based on this code here, or on your own understanding of how we create trees in a random forest, can somebody tell me, let's take a few seconds, have a read, have a think, and then I'm going to try and come up with a way of saying, how do you create a tree in a random forest?
Does the tree have to make a sound? Okay. So, index, right? Index is coming from that random seed thing we have. Permutation, okay. And then length of y, how many targets we have. And that's like an index of sample size. Okay, so we just have the index, I don't know why, what for, and then we return a decision tree, x, y. Is that an or is that a pipe? NumPy array self, I don't know what this is.
Okay, who wants to tell me? Anybody else? Okay, Tyler's got close to the mic.
You take your, you're essentially taking a random sample of the original data, and then you're just constructing a tree, however that happens.
So construct a decision tree,
So it's picking, this part is picking an index wherever, and then you start with the one tree, or like, is it a split? Yeah. Oh, one tree, not leaves. Okay.
a non-random tree from a random sample of the data. Okay, so again, like we've done.
I don't know, but there's like a line here. Do you see it? Right under the sample size.
Delayed any actual thought process here. We've basically said, okay, we could pick some random IDs. This is a good trick to know. If you call np.random.permutation passing in an int, it'll give you back a randomly shuffled sequence from 0 to that int, right? And so then if you grab the first colon...
It was his mouse? Wow, I feel bad for myself. It was... No, my cursor is the you know, an arrow. It was his, not mine. See, that's why I was moving around. I was like, why is this here? What's the reason for this? Okay, this is quite fun. Let's continue.
N items of that, that's now a random subsample. So this is not doing bootstrapping, we're not doing sampling with replacement here, which I think is fine. You know, for my random forest, I'm deciding that it's going to be something.
We spend quite some time comparing the lengths of... Yeah, literally, that's also what it reminded me of. That was fun. We learned a lot.
Where we do subsampling, not bootstrapping. Okay, so here's a good line of code to know how to write, because it comes up all the time. Like I find in machine learning, most algorithms I use are somewhat random, and so often I need some kind of random sample. Can you pass that, Tyler or Chenchi?
Won't that give you one extra? Because you said it'll go from 0 to length.
No, so this will give you, if len_self.y is of size n, this will give you n, a sequence of length n, so 0 to n minus 1.
Okay.
And then from that, I'm picking out :self.sample size, so the first sample size IDs.
I have a comment on bootstrapping. I think this method is better because we have chance of giving more weights to each observation, or am I thinking wrong?
No, I mean, I think for bootstrapping, we could also give weights.
I mean, weighing single observations more than they are, like, without wanting that weight, because when bootstrapping with replacement, we can have a single observation and duplicates of it in the same tree, which will give...
It does feel weird, but I think... I'm not sure that the actual theory or empirical results backs up our intuition that it's worse. It would be interesting to look back at that, actually.
I don't know what he meant.
Personally, I prefer this because I feel like most of the time we have more data than we want to put in a tree at once. I feel like back when Bryman created random forests, it was 1999, it was kind of a very different world, you know, where we pretty much always wanted to use all the data we had. But nowadays, I would say that's generally not what we want. We normally have too much data. And so what people tend to do is they'll like fire up a Spark cluster and they'll run it on hundreds of machines, when it makes no sense, because if they had just used a subsample each time, they could have done it on one machine. And like the overhead of like Spark is a huge amount of I/O overhead. Like I know you guys are doing distributed computing now. If you've looked at some of the benchmarks, yeah, exactly. So if you do something on a single machine, it can often be hundreds of times faster because you don't have all this I/O overhead. It also tends to be easier to write the algorithms. Like you can use
less communication between devices and making sure that things are synced. True.
It's like sklearn, easier to visualize, cheaper, so forth. So like I almost always avoid distributed computing, and I have my whole life. Like even 25 years ago when I was starting in machine learning, I still didn't use clusters because I always feel like whatever I could do with a cluster now, I could do with a single machine in 5 years' time. So why don't I just focus on always being as good as possible with the single machine? You know, and that's going to be more interactive and more iterative, and work for me.
That's really cool.
Okay, so again, we've like delayed thinking to the point where we have to write decision tree. And so hopefully you get an idea that this top-down approach, the goal is going to be that we're going to keep...
Even decision tree isn't something that's already there, something that he has to make. That's cool. So this is a random sample of the data passed to the decision tree, right? It's one... Here it says indexes, not one index. I thought it's one index, but I mean indices if you want to be particular about it. And then here we're saying range, an array of, for the sample size.
Keep delaying thinking so long that we delay it forever. But eventually we've somehow
love
written
it.
the whole thing without actually having to think, right? And that's kind of what I need because I'm kind of slow, right? So this is why I write
I feel like he's talking to my soul.
code this way. And notice, like, you never have to design anything. You know, you just say, hey, what if somebody already gave me the exact API I needed? How would I use it? Okay, and then, okay, to implement that next stage, what would be the exact API I would need to implement that? Right? You keep going down until eventually you're like, oh, that already exists. Okay, so this assumes we've got a class called decision tree, so we're going to have to create that. So a decision tree is something, so we already know what we're going to have to pass it, because we just passed it, right? So we're passing in a random sample of x's, a random sample of y's,
Indices.
Indexes is actually, so we know that down the track, so I've got to plan a tiny bit. We know that a decision tree is going to contain decision trees, which themselves contain decision trees. And so as we go down the decision tree, there's going to be some subset of the original data.
It's decision trees all the way down. I'm funny.
Data that we've kind of got. And so I'm going to pass in the indexes of the data that we're actually going to use here. Okay, so initially it's the entire random sample, right? So I've got the whole...
Is this like the idea of a table having their parent table with them? Parent ID, almost?
Let's see. I've got the whole range, and I turn that into an array. So that's 0, the index is from 0 to the size of the sample. And then we'll just pass down the min leaf size. So everything that we got for constructing the random forest, we're going to pass down to the decision tree, except of course num trees, which is irrelevant for the decision tree. So again, now that we know that's the information we need, we can go ahead and store it inside this object. So I'm pretty likely to need to know how many rows we have in this tree, which I generally call n. How many columns do I have, which I generally call C. So the number of rows is just equal to the number of indexes we were given, and the number of columns is just like however many columns there are in our independent variables. So then we're going to need...
Shape 1 means column. Okay. So it's not len. Got it.
This value here. We need to know for this tree, what's its prediction, right? So the prediction for this tree is the mean of our dependent variable for those indexes, which are inside this part of the tree, right? So at the very top of the tree, it contains all the indexes.
Yes.
Right? I'm assuming like by the time we've got to this point, remember, we've already done the random sampling, right? So when we're talking about indexes, we're not talking about the random sampling to create the tree. We're assuming this tree now has some random sample. Inside decision tree, this is one of the nice things, right? Inside decision tree, whole random sampling thing's gone, right? That was done by the random forest, right? So at this point, we're building something that's just a plain old decision tree. It's not in any way a random sampling anything. It's just a plain old decision tree.
Okay.
Right? So the indexes is literally like which subset of the data have we got to so far in this tree. And so at the top of the decision tree, it's all the data. Right? So it's all of the indexes. Okay? So all of the indexes. So this is therefore all of the dependent variable that are in this part of the tree, and so this is the value, mean of that. Does that make sense? Anybody got any questions about that?
No.
So, yes, can you pass it to Chen-Shi?
What I will have a question about is how are we going to do the split, which I don't think we're there yet, and how the indices change with that, because we're doing the mean right now, first leaf, for everything, and that makes sense.
Actually, just to let you know that a large portion of us don't have a OOP experience.
Okay,
Yeah,
sure.
just for
I
So, so a quick OOP primer would be helpful.
Sure.
Great.
I
Yeah,
love OOP,
okay.
but sure.
Um,
Remind me.
Who has done object-oriented programming in some programming language?
Me.
Um, so you've
C.
all used actually lots
I've
of
like actually studied OOP in the first that I studied, and I think it was in C. Ooh, don't remind me. And then later in Java. Ah, you too. Woo. Class here is good. I wouldn't say we're the average sample, but we're good.
object-oriented programming in terms of using existing classes, right? So every time we've created a random forest, we've called the random forest's constructor, and it's returned an object, and then we've called methods and attributes on that object. So fit is a method. You can tell because it's got parentheses after it, right? Or else
You've I don't want to say passed beyond me, but like you're ahead of me. Can you see this? Let me click it a couple of times. Yay, that was for you. Cool. C++, Java, and I think I'm not sure mine was C or C++. I think it was C++ actually. Yeah, definitely C++. And then Java. But Python, I've been using it, like object-oriented, but I didn't study it exactly in school. So good job.
Yeah, OLB score is a property or an attribute. Doesn't have parentheses after it. Okay, so inside an object there are kind of two kinds of things. They're the functions that you can call. So you
and then
you have
private
object
ones.
dot function parenthesis arguments, or there are the properties or attributes you can grab, which is object dot and then just the attribute name with no parentheses. So when and then the other thing that we do with objects is we create them. Okay, we pass in the name of the class, and it returns us the object, and you have to tell it all of the parameters necessary to get constructed.
I think like this recap is going to go over like I wouldn't say a lot of people, but like some people's heads, because it feels intuitive like when you use it, but I don't think it's that easy to explain to someone who doesn't. I don't know, maybe it is, I don't know.
So let's just copy this code and see how we're going to go ahead and build this. So the first step is we're not going to go m equals random forest regressor. We're going to go m equals tree ensemble. We're creating a class called tree ensemble. And we're going to pass in various bits of information. Okay. So maybe we'll have 10 trees, sample size of 1,000, maybe a min leaf of 3. Right? And you can always like choose to name your arguments or not. So when you've got quite a few, it's kind of nice to name them so that just so we can see what each one means. It's always optional. Right? So we're going to try and create a class that we can use like this. And then I'm not sure we're going to bother with .fit because we've passed in the x and the y. Right? Like in scikit-learn, they use an approach where first of all you construct something without telling it what data to use, and then you pass in the data. We're doing these two steps at once. We're actually passing in the data, right? And so then after that, we're going to be going.
Yeah, I saw it in the Titanic one. It was like, here's all the data. Do this. No, actually, there wasn't. Here's all the data. It was here's the settings for the model, and then here's x and y, which is what this style is, but he's not doing it that way.
M dot, so we're going to go creds equals m dot predict, passing in maybe some validation set. Okay, so that's the API we're kind of creating here. So this thing here is called a constructor. Something that creates an object is called a constructor. And Python, there's a lot of ugly, hideous things about Python. One of which is it uses these special magic method names. Underscore init underscore is a special magic method.
I did say that's mean a second ago. Now I agree with him. When I first started with Python, I was like, what the hell is this? Like, I get it. We have main in other languages. Yeah. I think it's like main, right?
Method it's called when you try to construct a class.
It's a constructor. Oh, okay. I guess, okay, that's not main. I think Python already has main. Anywho, it's a function thing.
So when I call tree ensemble parenthesis, it actually calls tree ensemble dot. People say dunder init. I kind of hate it, but anyway, dunder init. Double.
Like initialize it.
Underscore init, double underscore, dunder init. So that's why we've got.
It's called dunder, double underscore. Quicker would say underscore. I hadn't heard that. Like, I'm actually hearing this for the first time. Dunder. It sounds really Australian, doesn't it? I don't know why I'm like down under, dunder. Okay.
This method called dunder init. Okay, so when I call tree ensemble, it's going to call this method. Another hideously ugly thing.
I trust you. Blame the whatever lag there is between us. But I didn't know about it. Thank you.
About Python's OO is that there's this special thing where if you have a class, and to create a class, you just write class in the name of the class. All of its methods automatically get sent one extra parameter, one extra argument, which is the first argument.
Self.
And you can call it anything you like. If you call it anything other than self, everybody will hate you and you're a bad.
ISP? Yeah, really? We should blame the ISP?
Bad person. Okay, so call it anything you like, as long as it's self. Okay, so that's why you always see this. And in fact, I can immediately see here, I have a bug. Anybody see the bug in my predict function? I should have self, right? I always do it, right? So anytime you try and call a method on your own class and you get something saying you passed in 2 parameters and it was only expecting 1, you forgot self, okay? So this is a really dumb way to add OOP to a programming language, but the older languages like Python often did this because they kind of needed to, they started out not being OO and then they kind of added OO in a way that was hideous.
But is Python an old language? Maybe compared to the baby languages.
The ugly. So Perl, which predates Python by a little bit, kind of, I think, really came up with this approach, and unfortunately other languages of that era stuck with it. So you have to add in this magic self. So the magic self now, when you're inside this class...
Isn't the idea of self the same idea of this in, let's say, C++, C#, stuff like that?
You can now pretend as if any property name you like exists. So I can now pretend there's something called self.x. I can read from it, I can write to it, right? But if I read from it and I haven't yet written to it, I'll get an error. So the stuff that's passed to the constructor gets thrown away by default. Like there's nothing that says you need to this class needs to remember what these things are. But anything that we stick inside self,
reference to the current object, yeah. So same as this. I think this is also used in Java. Am I right?
It's remembered for all time. You know, as long as this object exists, you can access it. It's remembered. So now that I've gone, in fact, let's do this, right? So let's create the tree ensemble class, and let's now instantiate it. Okay. Of course, we haven't got x. We need to call x train, y train.
Eh? Error.
Okay,
Decision
decision
tree.
tree is not defined. So let's create a really minimal decision tree. There we go. Okay, so here is enough to actually instantiate our tree ensemble. Okay, so we've defined the init for it. We've defined the init for decision tree. We need decision tree's init to be defined because inside our ensemble init, it called self.createTree, and then self.createTree called the decision tree constructor, and then decision tree constructor basically does nothing at all other than save some information, right? So at this point, we can now go m dot, oh, sorry. Okay, and if I press tab at this point, can anybody tell me what I would expect to see? Pass it to Taylor. Chenchi, could you pass that to Taylor?
We would see a drop down of all available methods for that class.
Okay, which would be?
In this case, so if M is a tree ensemble, we would have create tree and predict.
Okay. Anything else?
Ah.
What? Oh yeah, and as well as Ernest whispered, the variables.
As well, yeah. So the variable
X, Y, sample size, and min leaf. Do you have some? Now I'm worried about public and private and stuff like that. Inherited stuff like that.
Could mean a lot of things. We'll say the attributes. Yes. So the things that we put inside self. So if I hit tab, right, there they are, right? As Taylor said, there's create tree, there's predict, and then there's...
You can hit tab? It's not... okay.
Everything else we put inside self, right? So if I look at m dot min leaf, if I hit shift enter, what will I see?
3.
Yeah, the number that I just put there, I put min leaf is 3, so that went up here to min leaf. This here is a default argument, so it says if I don't pass anything, it'll be 5, but I did pass something, right? So it's 3. Self.min leaf here is going to be equal to min leaf here. Okay? So something which, because of this rather annoying way of doing OO, it does mean that it's very easy to accidentally forget.
Yeah, to assign.
To do that, right? So if I don't assign it to self.min leaf, right, then I get an error. And so here, tree ensemble doesn't have a min leaf. Right? So how do I create that attribute? I just put something in it. Okay. So if you want to, if you don't know what a value of it should be yet, but you kind of need to be able to refer to it, you can always go self.min leaf equals none, right? So at least it's something you can read, check for noneness, and not have an error.
Okay.
Great.
Check for noneness.
Now,
that's a new word.
Interestingly, I was able to instantiate tree ensemble, even though predict refers to a method of decision tree that doesn't exist. And this is actually something very nice about the dynamic nature of Python, is that
unless you call it, it doesn't check for the error?
Because it's not like compiling it, it's not checking anything unless you're using it.
Using it, yeah.
So we can go ahead and create decision_d.predict later, and then our instantiated object will magically start working. Right? It doesn't actually look up that method's details until you use it. And so it really helps with top-down programming. Okay, so when you're inside a class definition, in other words, you're at that indentation level, indented one in, so these are all class definitions. Any function that you create, unless you do some special things that we're not going to talk about yet, is automatically a method of that class. And so every method of that class magically gets a self passed to it. So we could call, since we've got a tree ensemble, we could call m.createTree, and we don't put anything inside those parentheses, because the magic self will be passed. And the magic self will be whatever m is. Okay, so m.createTree returns a decision tree, just like we asked it to, right? So m.createTree.idx.
But decision tree hasn't been created, so that's why it's whatever this is.
XS will give us the self.idxs inside the decision tree.
Ooh.
Okay, which is set to np.arrange range self.sample size. Okay. Why, as data scientists, do we care about object-oriented programming? Because
it's easy to understand. Like, it's very intuitive and logical, or am I wrong?
a lot of the stuff you use is going to require you to implement stuff with OOP. For example,
because it's required? Okay, I didn't think that would be the answer.
Single PyTorch model of any kind is created with OOP. It's the only way to create PyTorch models.
Okay.
Good news is, what you see here is the entirety of what you need to know. So this is all you need to know. You need to know to create something called init, to assign the things that are passed to init to something called self, and then to stick the word self after each of your methods. Okay. And so the nice thing is, like, now to think as an OOP programmer is to realize you don't now have to pass around X, Y, sample size, and min leaf to every function that uses them.
Yeah, I think I didn't know that. You just get it from self. I think I remember a professor asking us this question. I said, because it's the closest paradigm to real life, everything is an object and objects interact with each other. It was the best answer. I absolutely agree with you. I can't give you a clap, so I'll give you this. Yeah. It feels right. I agree with you.
By assigning them to attributes of self, they're now available like magic. Right? So this is why OOP is super handy. If you're particularly, I started trying to create a decision tree initially without using OOP and try to keep track of what that decision tree was meant to know about was very difficult. Whereas with OOP, you can just say inside the decision tree, self.indexes equals this, and everything just works. Okay, that's great. So we're out of time. I think that's great timing, because there's an introduction to OOP, but this week, next class, I'm going to assume that you can use it, right? So you should create some classes, instantiate some classes, look at their methods and properties, have them call each other and so forth until you feel comfortable with them. And maybe for those of you that haven't done OOP before and find some other useful resources, you could pop them onto the wiki thread so that other people know what you find useful. Great.
Okay.
Thanks, everybody.
Thank you. So, I feel like I should do the Jeremy Howard way of saying, okay, that's it. We're done. Let's go. Yeah, this was really, really, really fun. I feel like I actually understood stuff. So, there are a few things that I want to discuss before we go. Was there anything before I discuss the other thing? Yeah, it's cool that we finished lesson 5 today. Yeah, so here's the plan. I've been streaming for 2 weeks, every day, non-stop. And starting October, which is today, I think it's not 100% confirmed yet, but there are some newer responsibilities that are coming my way. And I think I need some time for myself, even though... Thank you. Even though I really, really, really need to learn this as soon as possible. I need this. This isn't something I'm doing so that you guys learn. It's something that I need to learn before the school year starts. Oh yeah, there is something I wanted to say. Yeah, I'll say it next week. It wasn't important. It had to do with the lesson. So I have an idea, which is to increase the frequency of the streams from 7 times a week to 4 times a week, and have those other times to do, stuff that I need to work on. It might even be, I don't know, it might even be like making a video, because I don't have a time to make videos for YouTube. I mean, I do technically have time, but I want to live my life and be with my family, so I call it not having time. So yeah, I don't want to give everything, I want to give as much as I need to, and as much as I can. So I think I will put a schedule on thank you, that's really kind of you. I will put a schedule in the community tab later. I don't think I can do that right now, but first of all, there will be a stream tomorrow, so no worries, inshallah. I'm not giving 100% promises, so I will put inshallah with it, and then I'll probably put it on Twitter as well. The current schedule is Friday and Saturday, both days are stream days, and then the weekdays, Sunday off, Monday on, Tuesday off, Wednesday on, Thursday off. So the weekdays are one every other day, but weekends, both days I can stream, inshallah. So that's the plan. I hope we can do it. I know we will lose the speed that we've been taking this course, 5 lessons in over 2 weeks, but yeah, I will need the time starting today, even though I will stick to my plan of Monday on, which is tomorrow. Okay, I gotta go. I really enjoyed today, because I think I wouldn't say I can recreate it for you right now, but I did understand almost a lot of the things that he said, and surprisingly the internet was pretty good, so that was also fun. Yeah, we can go now. So I hope you have a lovely week ahead of you, and inshallah see you tomorrow. So I will end the stream in 5. Yeah, that surprised me. In 5, 4, 3, 2, 1. Have a lovely rest of your day, and goodbye. Thanks. Bye. Blast off.